Hello everyone, I'm Miles. Suppose the average time for employees to complete a task is 50 minutes. Now, with the introduction of a huge training program, we want to know if it can actually reduce the average completion time. We randomly selected 36 employees with a sample mean of 47.8 minutes and a sample standard deviation of 6 minutes. Before testing, let's check 3 assumptions. First, it's a simple random sample. Second, observations are independent. Third, data is approximately normal, or the sample size is large. Here, n is 36, which is over 30. The sampling distribution of the sample mean is approximately normal. The null hypothesis is H0, mu equals 50, and the alternative is HA, mu is less than 50. The word reduce indicates this is a left-tailed test. With alpha at 0.05 and unknown population standard deviation, we use a one-sample t-test. T is 47.8 minus 50 over 6 divided by the square root of 36, equaling negative 2.2. Degrees of freedom are 35. P is 0.017, which is less than 0.05, so we reject the null. At the 5% level, there is sufficient evidence that the training reduces average completion time below 50 minutes. Note that a p-value of 0.017 doesn't mean there's a 1.7% chance the null is true. The correct interpretation is that if H0 is true and the true average time is 50 minutes, then the probability of obtaining 47.8 minutes or lower due to random sampling alone is about 1.7%. Therefore, the p-value measures how surprising the data is if H0 is true, rather than the probability that H0 is true. Next, let's discuss 2 very important types of errors. The critical sample mean corresponding to alpha equals 0.05 is approximately x, which equals 48.36. When x is less than or equal to 48.36, we reject H0. Otherwise, we do not reject H0. If H0 is actually true in reality, but we reject it, this is a type 1 error, also known as a false positive, and its probability is controlled by alpha, which is 5%. Now, let's assume the training is indeed effective and the true mean time is mu equals 47. In this case, H0 is false. If we still fail to reject H0, we have committed a type 2 error, which is a false negative. With the same critical value, the type 2 error probability, beta, is p of x greater than 48.36. Since mu equals 47 corresponds to a z-score of 1.36, beta is 8.8%. This means even with a real effect, there's an 8.8% chance we miss it. When mu is 47, there are only 2 outcomes. We either miss the effect with probability beta, or correctly detect it with probability equal to the power. Therefore, the power equals 1 minus beta, which is 91.2%. It becomes clearer when we put the statistical decision and the reality together. Rejecting a true H0 is a type 1 error, and failing to reject a false H0 is a type 2 error. Correctly rejecting a false H0 is the statistical power. To summarize, the p-value asks, if H0 were true, how surprising would this data be? Alpha controls false positives, beta is the chance of missing a real effect, and power, or 1 minus beta, is the chance of correctly detecting one.